Partial pressures and mole fractions. A 12.5 liter scuba diving tank is filled with a helium-oxygen heliox mixture containing 24.2 grams of helium and 4.32 grams of oxygen at 298 K. Calculate the mole fraction and partial pressure of each component in the mixture and calculate the total pressure. In this problem, we are given a mass of helium, that is equal to 24.2 grams, given a mass of oxygen, 4.32 grams. We're given a volume of the tank, that is 12.5 liters, and we are given a temperature that is 298 K. We're being asked to find the mole fraction, which we'll symbolize by a capital X, of helium, the mole fraction of oxygen, the partial pressure of the helium, the partial pressure of the oxygen, and the total pressure. In our conceptual plan, we're going to take the mass of each of the components, helium and oxygen, and convert them to moles. After we do that, we can determine the mole fraction of each using the definition of mole fraction, and then we can calculate the total pressure, and then finally calculate the partial pressures. So in order to determine the number of moles of helium, our relationship that we'll use is the molar mass of helium. And the molar mass of helium is 4.00 grams per mole. To determine the number of moles of oxygen, we need the molar mass of oxygen. And that is 32 grams per mole. Now, relationship C is simply the definition of mole fraction. Where mole fraction X of any component, let's just call it component A, is the number of moles of that component divided by the total number of moles that are present. Relationship D that we are using to calculate the total pressure is simply the ideal gas law. in which the total pressure times the volume is equal to the total number of moles of gas times the gas law constant R times temperature, of which the gas law constant R is 0.08206 liters times atmospheres per mole times kelvins. Finally, in order to calculate the partial pressures, we are using a relationship that's derived from Dalton's law of partial pressures. And that is that the partial pressure of any given component can be found by taking the mole fraction of that component times the total pressure. So now let's apply this information and solve the problem. So in our conceptual plan, first thing we'll do is to convert each mass to moles. So we have 24.2 grams of helium, and 1 mole of helium is 4.00 grams of helium, and so we have 6.05 moles of helium. Now let's scroll down and now we'll determine our moles of oxygen in the same way. We have 4.32 grams of oxygen, and 1 mole of oxygen is 32.00 grams of oxygen. So this is 0.135 mole of oxygen. The next step in our conceptual plan is to now use these moles to calculate mole fractions. The mole fraction of helium is equal to the moles of helium, which we just calculated, divided by the moles of helium plus the moles of oxygen, which we just calculated. So we have 6.05 mole of helium divided by 6.05 moles of helium plus 0.135 mole of oxygen. And this gives us 0.97817 as our mole fraction, which is good to the third significant digit. The mole fraction of oxygen is found in a similar manner. We'll take the number of moles of oxygen now and divide this by the number of moles of helium plus the number of moles of oxygen. And this is equal to 0.135 mole of oxygen divided by 6.05 moles of helium plus 0.135 mole of oxygen. So this is equal to 0.02187. Again, this is good to the third significant figure. The next step in our conceptual plan is to determine the total pressure. Total pressure is equal to the moles of helium plus the moles of oxygen times RT over V. So this is equal to 6.05 mole plus 0.135 mole times 0.08206 liters times atmospheres per moles times K times our temperature of 298 K. And this is divided by our volume, which is 12.5 liters. So our moles will cancel, our temperature will cancel, and our volume will cancel, leaving us an answer in atmospheres. So our total pressure is equal to 12.099 atmospheres. Again, this number is good to the third significant figure. So our partial pressure of helium is equal to the mole fraction of helium times the total pressure. This equals 0.97817 times 12.099 atmosphere, and this is equal to 11.8 atmospheres. Our partial pressure of the oxygen is the mole fraction of oxygen times the total pressure, and this is 0.021827 times 12.099 atmosphere, and this is equal to 0.264 atmosphere. Let's check our answers. We were asked to calculate partial pressures in atmospheres. The units are correct. And looking at the magnitudes, they also seem to be quite reasonable.